Welcome to this tutorial, guys. We're going to continue with solutions to nonlinear equations, and we've got another interval method that we are going to go over. So in the last video, we went over the bisection method. And we used, we did an example of f of x equals x squared minus x minus 2 and solved for the root. And we found that the root was somewhere between 1.75 and 2.125. Okay, so now we will use the false position method, and this was for 3 iterations. So we will do 3 iterations of the false position method as well and see how close our answer is and compare the two. Okay, so the false position method uses a similar idea to the bisection method, where we have f of a, f of b, and f of c, where f of c is somewhere between a and b. So if we have just a random sketch here, a, b, and c will be somewhere in the middle. If you remember, with the bisection method, c was always in the middle of a and b, but with the false position method, c is not always between a and b. It can be slightly left, it can be right of it. It doesn't really matter. C can be anywhere. It depends on the function. Okay, so how do we work out c this time? Okay, so for c, to figure out c, we have an equation which is the following. C is equal to a times f of b minus b times f of a all over f of b minus f of a. Okay, and yeah, so that's basically all you really need to know. This is the most important equation for this section, and we can get straight into equation just to show you how, into an example, just to see how this method works. Okay, so we're going to use the same example as last time. So we're going to say f of x is equal to x squared minus x minus 2. Okay, now similarly, last time I drew a little number line. This time I'll draw one as well, slightly smaller, but we have 4. Okay, so the restrictions last time was between, we want to find the root between 1 and 4. Okay, so we have 1 and 4. So again, like last time, we need to make sure that these two have opposite signs, and we know that they do. F of 1 is equal to minus 2. F of 4, if we substitute 4 into this equation, is equal to 10, so they have opposite signs. Okay, so now we can work on getting C1. So let's just put the signs in there, plus minus. Now we can work on getting C1. So C1, which would be our first iteration, is going to be, so the way I remember it is, if we make sure that we have the negative value here and the positive value here, looking at these signs here, you write it out as I've written it, then what we do is we multiply these two together, we multiply these two together, so subtract them, and then you minus these two at the denominator. So let's see if I can make that a bit more clear, but let's go into it. So we will have, so it's going to be 1 times 10, which is the multiplication of that, and the equation says it's minus, so minus 2 times 4 over the denominator, which is this number minus that number, 10 minus 2. Okay, and the solution comes out as 3 over 2. So C1 is 3 over 2. Now what we do is we plug C1 into the equation. So f of 3 over 2 is equal to, if we plug it in, we get minus 5 over 4. So once again, we have a negative number. So that means that, so somewhere here, a negative number. So we're still working with this interval here. So we're still working with 4. So we have f of 4, which is equal to 10 still. And now we can work on getting C2. Okay, so C2, using the same rule, it's 10, or 3 over 2 times 10. Let's just draw that nicely. 3 over 2 times 10 minus 5 over 4 times 4 all over 10 minus 5 over 4. So that becomes a plus. Okay, and what we have is C2 is equal to minus positive 16 over 9. Okay, now we plug C2 in, so f of 16 over 9 is equal to minus 50 over 81, and we're still working with f4 because again we have a negative number and a positive number, so we have 10 here. Okay, and we do the same method to get C3, and we come out with C3 equaling 1,906,977. So that would be our answer for 3 iterations. Okay, and if we compare this to the bisection method gave us quite a large range over here compared to the forced position method, which tells us it's approximately equal to 2, which is actually the interval. If we did this question analytically, we would find that x is equal to -1 and x is equal to 2 at their roots. So our answer using the forced position method is better. Okay, and the reason why we would use the forced position method is the intervals that it goes down in is not always a half compared to the bisection method, which it is always a half. So in this case, we get to the root much faster than the bisection method. And the root usually approaches from one side. So what that means is that we usually, if the root is at 2, which we know that it is, if the actual root is at 2, the forced position method will work its way from either side. So it could work its way from this side and get closer that way, like it did in this case. In this case, it started at 1.5 essentially and moved itself that way all the way to 1.90 or whatever. But there are some cases in which the root may start, C1 may start somewhere on this side closer to 4 and work itself that way with the bisection method. Okay, yeah, that's about it for this video. In the next video, we will get into fixed position methods, and the one that we will focus on will be Newton's method. Okay, so thanks for watching, guys.